talked about continuity. And a function is continuous if that function is defined at that x value. So there's a point there. If the limit exists, so the limit from the left equals the limit from the right, and if the limit and that point meet at the same place. So it's easy to see from a graph if it's continuous or not. It's not always easy to see on an equation. So I posted this sheet also just in case you want to play along and you don't want to write out the whole thing. So are the following continuous? So let's start with f of x equals 1 over x plus 2. Is this function continuous at x equals negative 2? Well, we should know that this is going to be a rational function. And at negative 2, we have a vertical asymptote. So at that point, when you have a vertical asymptote, you get that swoop, swoop. So no, f of x is not continuous at x equals negative 2. This is considered infinite discontinuity. The other main reason is if I try to plug in negative 2, my answer is undefined, so there is not a point at that location. So it breaks rule number 1 for continuity. So what about this next one? This is a piecewise function. We have the rule for when x is greater than 2, when x is equal to 2, and when x is less than 2. So let's go through that, the definition of continuity step by step. F is continuous. First of all, does f of a, or in this case g of a, exist? Well, g of 2, so when x is 2, I get negative 5. That's awesome. So step 1 works. Step 2 is the limit has to exist. So we have to check the limit from the left and the limit from the right. So for step 2, I need to do the limit as x approaches 2 from the left. Now that's going to be which rule? Well, left would be less than 2, so it's following this rule. So we're going to plug 2 into this rule. So that's going to be 3 times 2 minus 7. That's a negative 1. I also need to check the limit as x approaches 2 from the right. That's going to be when x is bigger than 2. So that's this rule. That's 2 minus 3. So the limit from the left and the limit from the right are the same thing. The limit as x approaches 2 from either direction is negative 1. So we've passed the first condition. We do have a point when x is 2. We do have a limit when x is 2, but they're not the same thing. So what that means is we have a situation like this where the limit from the left and the limit from the right meet, but it's not where the point is. So step 3, g of x is not continuous at x equals 2 because the limit does not equal the point. So that's kind of our process with a piecewise function. First, we have to check to make sure the point exists. So here we've got when x is 3, So which of these contains 3? Well, that would be the second one. So h of, whoops, I forgot to put step 1. H of 3, I'm going to plug into the second function. So that's going to be 3 squared minus 2 times 3. That's going to be 3. That's also greater than, that's also my right limit. So I'm going to go ahead and write that. The limit as x approaches 3 from the right is also 3. So we're looking pretty good here. Now we need to check the limit from the left. And that's going to be the other piece of the piecewise. So 3 times 3 minus 5, that is 4. So the limit from the left does not equal the limit on the right. So I'm going to put a therefore. The limit as x approaches 3 of g of x does not exist. The limit from the left does not equal the limit from the right. So, g of x is not continuous. What kind of continuity would that be for each of these? Let's talk about the difference there. It's not continuous at x equals 3. Okay, so on this one, the limit did exist, but it wasn't the same as the point. So if the limit did exist, that would be a removable discontinuity. There's a hole there. Now this one, the limit from the left didn't meet the limit from the right, so this would actually be a jump discontinuity. Now notice the difference on this one. I did not state what x value we're looking at. So let's think about the domain of this function. This function is defined for everything except for x equals 1. F of x, so everywhere else it would be okay, right? Is continuous on its domain of all x's such that x is a real number where x can never, ever, ever be 1. If you're not used to that notation, that set notation, some pre-calc classes teach that, some don't. The main thing is it's continuous everywhere except for 1. So since x cannot be 1 is the actual domain, it is continuous on the rest of its domain. Okay. On 5, we have an extra variable here. And the question states, for what value of c is f of x continuous from negative infinity to infinity? So what would have to be true for f of x to be continuous? Well, the left side would have to match where the right side's going. So if I plugged in 2 into the left side, it would have to match what happens when I plug in 2 on the right side. In other words, the limit as x approaches 2 from the left must equal the limit as x approaches 2 from the right. So what I'm going to do is plug 2 into the left piece. And set that equal to plugging 2 into the right side piece. So this is 4c plus 4 equals 8 minus 2c. And now we just have an equation to solve. How nice. Add 2c over here, so I get 6c equals 4. So c would be 2/3. And those are some examples of what kind of practice problems you'll see on the exercises.